So hello and welcome back. Today is lecture 4-1B on probabilistic sensor models, and our learning objectives include the following. Describe probabilistic measurement models. Describe various types of sensors on a mobile robot. All of that was done in lecture 4-1A. Discuss using ray casting to determine the probability of a given shape for a map given a robot pose. Devise maximum likelihood for noise parameters for a measurement model in a mixture model. Also discuss likelihood fields measurement models for rangefinders. And finally, describe the map matching, beam-based, and feature-based measurement model. So recall that a lot of the content from this course comes from probabilistic robots. Recall that a lot of the content from this course comes from the Probabilistic Robotics course created by Dieter Fox, Wolfram Burgard, and Sebastian Thrun. And you can find more about their content as well as their textbook at probabilisticrobotics.org. Let's get started. So the beam-based proximity model is based upon thinking about the sensor data as a beam, as you would in a laser as opposed to a cone, which you would do with a sonar. So what is the probability that a robot reads 3.5 meters to a wall, given that the expected value or actual distance to the wall is 3 meters? So you would be given the map, you would be given the robot's pose, and it's the probability of z given x at time t in the map. Another way to think about it is it's the probability of a sensor reading z knowing the expected sensor reading. So the probability of reading a 3.5 given that we expect to get a 3. So in the beam-based proximity model, we model the error in the sensor as we did for motion models using a Gaussian distribution where z expected would be the mean of the Gaussian distribution. And of course, the error with respect to that measurement is going to end up being our standard deviation. So the probability of getting a hit given for that sensor z given xm is eta over 1 over the square root of 2 pi b e to the negative 1/2 z minus z expected squared over b. And this is just our Gaussian distribution formula that we have seen in previous lectures. Now, the model we use for unexpected obstacles, which means when there's more than one obstacle in the environment, is that it exponentially decays, where the first one will be the highest probability, and then each one after that would be a lesser probability, up until the expected measurement. And the formula we use for that is eta lambda e to the negative lambda z, where z is less than our expected measurement, otherwise it's a 0. For the beam-based proximity model, for any random measurement in the environment, that one has a uniform distribution where it's the probability of finding one moving object or dust or anything in the environment has the same probability. So that's the probability of a random value of a measurement z given x and m is just eta times 1 over z max. And our final one is our max range. So this would be like a sonar that has specular reflection or that goes off into hitting a large value and coming back, whether one exists or not. And so that's basically also a uniform distribution of just the probability of getting the maximum range value for the sensor. So it is eta times 1 over z small. So when we put all of these together, this is called our mixture probability density. And what you should see here is that we have the exponentially decaying part on the left, then we have the Gaussian distribution, then we have the uniform distribution, and then we have z max. And thinking about these as independent distributions, we then have a constant for each of them, and that's multiplied by each of their probabilities. So alpha hit, alpha unexpected, alpha max, alpha random, times the probability of a hit or unexpected or max or random. So this is how we determine our overall model for measurement uncertainty. And how do we get those parameters? Well, we would do sensor testing. So then we would then combine all the errors based upon their weighted sum. And we look at the different ways that they interact in an environment based upon the type of sensor error, as well as things like reflective surfaces in the environment. As we talked about before, specular reflection when it's not an incident angle that's dead on, or if it's a glass, a window, what kind of error you would get when a sensor tries to detect that. So how big are those individual parameters? Well, that all depends on the mean and the variance of that sensor data. So here are some examples of raw sensor data for a sonar and a laser where the mean reading is approximately 300 centimeters and the maximum range is 500 centimeters. So this random data looks as you would expect, where most of it is centered around 300 centimeters, which is our expected sensor measurement. And then it gets a little bit higher as we get away from it. It gets more dispersed, but with the sonar, you will see more of those max readings right at 500 centimeters. So that's where you may be getting back those false readings. So you would then use that as your model for your sensor data as well as for finding your measurement error. So this is how we calculate the model parameters to define the shape of the measurement likelihood from that data. So we would come up with some log of the likelihood of getting certain data. So if you're expecting a certain sensor measurement like 300 centimeters, but you're getting data at all these different values Z, then you plot those and you can use those to come up with a noise parameter that we use for modeling that particular sensor. And then you would search the space for these types of parameters. And there's several different kinds of algorithms for doing that. Some of those would be hill climbing, all which are beyond the scope of this course. And then you would deterministically compute the nth parameter to satisfy some normalization constant. So here's what you would do is you would take all of that sensor data, including the expected value, and then you would try to fit it to some model. And by finding the model that it fits to, that's how you come up with your noise parameter. So you would put the measurement data in these bins here for all these expected measurements, and then you would try to optimize the noise parameter that most closely matches the shape. And then you could use that as the sensor noise parameter that we then use in our model. So here's another example of what this looks like, where you plotted in 3D space of the expected value versus the measured value using our probability density function. And then you look at that vertical column and you would determine what's the probability of getting that sensor reading, knowing what our expected value is. And you could get that from this plot just by pinging the data a lot and getting all of this information and putting it on a graphic such as this. So here we see from our beam-based sensor model, as we said before, assuming independence, it's just going to be the product of the sensor reading given the robot's pose and the map location for all of these different values. So that's what we're showing here, where the probability of a measurement given the robot state and map is just going to be those multiplied together. So what this would look like is that if you have a robot moving through a hallway and you want to characterize that sensor data given a model for the sensor and all the different types of measurement noise, then over here on the right, we have a map of the world. And what it would give you is all the possible locations for that robot given the sensor reading. So we know the ground truth from the left because we know how we drove the robot through the hallway. But here on the right, what you would see is the probabilities that the robot actually is in a certain spot given the data that comes back. So each of those red dots represents the expected locations where those sensor readings could have possibly been taken. So for every beam measurement that I have from my sensor, I look at the probability on my plot given of what expected reading I thought I would have. And then I assume that each of those beams is independent, and I multiply all of those probabilities together to get the overall probability, where we see that the shape of that probability, once again, has our exponentially decaying part for all of the multiple objects that could be in the world. Then I have my expected reading with the Gaussian distribution. Then I have my uniform probability for any arbitrary object that I encounter in the world. And then I have my maximum range on the end as well. So now we also have to think about what about the angle? If you think about a sonar or laser that's rotating, then the angle to the obstacle will also influence this probability. So here we have a plot that shows the expected measurement, the actual measurement, and then we have the probability of the axis. So this is called ray casting to calculate the expected distance to the obstacle in the world, knowing that there's an angle of incidence here. So this makes the sensor model more accurate, but it also adds this third dimension where I now have to look at the bearing, not just the distance. So we're going to need more data in order to create our model, and that's what we have here. And then notice if this is a sonar array here, so that was sonar 0 on the previous slide, and this is now sonar 1. And notice that with every angle along that sonar array, the angle to the object or obstacle in the world is going to change, so it's going to change the overall shape as well. So every sonar, the data is going to look a little bit different because there's a different angle of incidence. And the more you do this, you may start to notice that the Gaussian area is not there anymore. So this adds to the complexity in this calculation because it won't always have that expected shape that you had where the expected value was based upon that Gaussian distribution. So in summary, when you have a beam-based model, do not get overconfident because obviously things like angle of incidence can change that probability. But on some level, you can justify using that Markov independence assumption, and we definitely want to use that because it actually makes it easier to calculate that value. So you can model some of that noise error by doing physical causes, such as looking at things in the world and the different types or mixtures of error or causes of error, like we looked at hitting on the object exactly, having random measurements, having maximum range errors, as well as having those expected errors and all of those, which have like the Gaussian distribution, the uniform distribution, etc. And we also assume independence between the different causes because that makes it easier for us to calculate the overall probability. And we can learn the parameters for the noise by looking at real data and know that different models will have different incident angles as well as sensor beams as they hit the obstacles. And this may also affect how we can model the probability of a sensor reading. And so we have to determine these expected distances as well by doing ray tracing. And notice that a lot of this can be pre-processed so that you don't have to do it at that time. As long as you have your sensor model, you can actually do that. But there will either be a trade-off between memory from pre-processing or computation time in real time if you do this in real time. And this concludes today's lecture on probabilistic sensor models. I hope to see you back. Have a robotastic day.